Welcome back. In this lecture, we will review some of the elementary concepts associated with electrostatic capacitors. You must have seen all these things in your high school, but it is just a way to refresh your memory because we'll be using these concepts in subsequent lectures on electrochemical double layer capacitors. So let's move on. So a simple capacitor from your high school times is referred to by this symbol. All you have is a metallic plate wherein one metallic plate has negative charge and the other metallic plate has positive charges in them. These two are separated either by vacuum or they can be separated by an insulator. And there is a specific distance between these two plates. So you would have seen that the capacitance is given by the charge that is stored in these plates divided by the voltage difference, potential difference between these two plates. To realize this energy storage mechanism, you have to have done electrical work and separated the charges. So Q is directly proportional to the voltage difference, and the capacitance in this case is a constant. It doesn't depend upon the voltage difference. You would have also derived the formula for capacitance from elementary electrostatics. So that goes as for this kind of configuration, capacitance is equal to dielectric permittivity of vacuum if there is no insulator between these two plates, epsilon naught times A, the area of the metallic plates, divided by D. This is the distance between them. If instead of vacuum, you have an dielectric material, let's say an insulator, of permittivity epsilon, relative permittivity is epsilon divided by epsilon naught. And you can write the capacitance for that capacitor with an insulator in between via this formula. So all these things you must have seen in your high school. As opposed to all these things, we would be referring to capacitors that depend upon the voltage. In this case, we would often talk about differential capacitance. We are not talking about Q by V. This is often called integral capacitance. This is called differential capacitance that goes as dQ by dV. This is most useful when capacitance depends upon the voltage. As the voltage difference between these two electrodes vary, the capacitance will also vary. So we often would be referring to differential capacitance given by this formula. We will also look at few other concepts. When capacitors are connected in parallel, what is important to realize is that the voltage difference across all the capacitors that are in parallel, the voltage difference is the same. Therefore, you can write the charge, overall charge stored, as the sum of charges in each of the capacitors that are connected in parallel. So once that is so, you can substitute Q, the formula for Q, as C times V, as the voltage is the same across all the capacitors that are in parallel. You can get to this formula. the formula for all the capacitors connected in parallel goes in this manner. As opposed to this, when capacitors are connected in series, what is important to realize is that the voltage drop across the entire bank of capacitors goes as V1, the voltage drop across the first capacitor, plus the voltage drop across the second capacitor, and so on. What's important to realize is that the charge across each of the capacitors that is in series, the charge is the same. And again, in this formula, once you use this formula, that is voltage is Q, which is the same across all the capacitors, divided by, in this case, let's say Q divided by C1 plus Q divided by C2, and so on. When you substitute this formula into this formula, you can cancel off C and you will get this formula. This is the overall capacitance for capacitors that are connected in series. These two formulae are irrespective of the different kinds of capacitors we would see. What we saw is the simple electrostatic capacitor. Even if you consider more complex capacitors like electrochemical double layer capacitor and electrolytic capacitors, these formulae are relevant or valid. The next kind of capacitor which we would discuss is the electrolytic capacitors. First, what is important to realize is that electrolytic capacitors are not electrochemical double layer capacitors, which we would see in the next lecture. But in this lecture, we are going to be referring to electrolytic capacitors. So as opposed to conventional electrostatic capacitors, the electrolytic capacitor have a greater structural feature. So, and the most dominant electrolytic capacitor is made up of anodized aluminum. So here, the anode of this anodized aluminum is shown. So what do you mean by anodized aluminum? So you have aluminum metal. On the surface of aluminum metal is aluminum oxide. Okay, aluminum covers the surface of metallic aluminum. This provides the dielectric constant. The thickness of this alumina is the D that we refer to in this context of conventional capacitors. So the charge is stored across this distance D. So this is the blown up part of this particular oxide layer and the adjacent metallic layer. So why do we do this? The essential design principle of electrolytic capacitors follows from the formula for a simple capacitor. So if you have the formula for a simple capacitance, the capacitance scales as A, and when D is decreased, capacitance increases. So if you look at this structure, this kind of corrugated structure goes towards increasing this area, and if this thickness is very less, then that goes here, you are increasing your capacitance. So the electrolytic capacitor, as opposed to simple electrostatic capacitors, has much higher surface area and much less D, both of which goes towards increasing C. There are other features. First is that this structure, this alumina structure, is fabricated via an electrochemical process called anodizing. That is why we talk about, refer to this as an electrolytic capacitor. So what happens is that an aluminum metal, when exposed to high oxidation potential, gets oxidized in an aqueous media to form alumina. So this is a specialized um, metal finishing or electrodeposition process for converting metal to an oxide, that is done at very high voltages. The voltages can be, let's say, even 100 volts and so on. That is the way you end up making this particular structure of a metal and a metal oxide on its surface. As opposed to conventional capacitors, the electrolytic capacitors have a polarity. So this anode, that is the electrode wherein there is this metal oxide interface or structure, always has a positive polarity. It is important that you don't connect this structure to this structure. This electrode should not be acting as a negative electrode. If you connect it to a negative electrode, this oxide will tend to get reduced. So it is important that this material, all this electrode, that is this metal oxide material, always acts as the anode of a electrolytic capacitor. As opposed to this, the conventional electrostatic capacitor didn't have a polarity. While you say that this is the negative polarity of this capacitor, you can switch. This is also a metal plate. This is also a metal plate. They are not typically compositionally different. Therefore, uh, you can switch this metal plate to be a positive electrode or this metal plate to be a negative electrode. It won't really make a difference. But as opposed to that, this structure has a polarity. This should be the anode, and the other electrode should be the cathode. In the next lecture, we will introduce the electrochemical double layer capacitor, which is the central capacitor or topic of the series of lecture. We will introduce that in the next lecture. Thank you.